Hey there, everybody. Welcome. This is part 2 of our projectile motion video series here. We really only have these 2 videos. So this one hopefully won't go too long, but I'm going to do kind of something similar to what I did before, where I'll have a couple of slides that just sort of introduce the concept, and then I'll go through 2 practice problems there towards the end. So that's always a good spot to take a break is when I'm doing the math part, right? Walk away, get some fresh air, get some exercise maybe. Anyway, so it'd be helpful if you had your calculators and all that kind of good stuff to help along here. Get some scratch paper to work on these, but that's where we're going here. So anyway, part 1, our first kind of foray into projectile motion, we only really took a look at projectiles that were launching just horizontally. So taking off from from a cliff, or just launching off of a tabletop or something along those lines, which works. I mean, it works fine. We learned about the idea that the horizontal motion is only governed by inertia, constant velocity. The vertical motion is governed by acceleration due to gravity. And we solved, kind of figured out some of our basic techniques, which is you solve component number 1, solve for time, you plug that time into component number 2, whichever one it is, and then you're solving for your missing item, whatever. The idea that if the question's asking you something about a horizontal answer, then you're going to start with the vertical components to kind of figure out what your time is. So with this, when we're talking about launching something vertically at an angle, or something up, different kind of ranges or different angles, the important thing to keep in mind here is that now our VI is not equal to 0. Our VI horizontally was never equal to 0, but vertically, when we did horizontal launches, our VI vertically was considered to be 0. That is no longer the case, and that's the really important thing that we have to take into account here. So when we're launching something upwards, it now has a VI at an angle, so that VI at an angle has got some X component to it and some Y component to it. Sounds like SOHCAHTOA to me. So that's one of the things that's really important to kind of keep in mind as we're working today, is that our different initial angles make a really big difference for how much of that initial velocity is vertical versus how much of it's horizontal. And you can see that on the screen right here, that if you've got a 45-degree launch angle, that's the middle red line, that you're basically equally X and equally Y. Right, so half of that velocity is horizontal, half of it's vertical. So you don't get maximum height, but you do end up getting maximum distance to it. When you're talking about the other types of versions to it, when you've got different angles to it, then if you're talking about going at that 60 or that 75-degree angle, now a lot of your velocity is going vertically. It gives it more vertical height, but then it doesn't have as much horizontal component to it. It's a different angle to it. So again, it's a little bit different in terms of how these two things sort of play together to give you an idea about altitude, which is the vertical component of your direction, and range, which is the horizontal component of your displacement. So let's take a look at how this kind of applies. So the first thing that we need to do is we need to take that VI, that initial velocity, and we need to turn that into the horizontal and vertical components. Again, SOHCAHTOA. In this particular case now, because we're launching it at an angle, VI and VIX are not the same thing. There's a VIX and a VIY. And again, it's just all about SOHCAHTOA to figure out which one's which. So if we've got our launch angle right there, that means that we have 2 different components to it, right? This would be VIY, and this would be VIX. And in terms of using your launch angle, we would say something about sine and cosine. VIX is going to tell something about the horizontal motion, and that's going to tell us about range. Again, how far downfield it's going to go. And oftentimes the way that these angles are designed, it's going to be the cosine of this, right? So we've got SOHCAHTOA, right? Cosine is equal to opposite over hypotenuse, right? So the way that we would solve for VIX, which is adjacent, right? And sine, sorry, what am I doing here? Guys, you got to stop me when I do this wrong. Sine is opposite over hypotenuse. I'm always used to doing that one first. So cosine is going to give us the adjacent side, CAH, right? So cosine of our angle is equal to the adjacent side, which is VIX, times the hypotenuse, which is VI. So this is going to be VI times cosine of theta. It's going to give us VIX. VIY is going to be VI times the sine of theta. Gives us VIY. Again, sine is the opposite side to it. So as we're dealing with our two components, the first thing that you need to do is kind of take that initial VI and turn it into its X and Y components. And then make sure that you clearly label them. Super important. Make sure you clearly label them, because this really is the biggest mistake that students make, is that they've got all these initial velocities and they start trying to mix and match them. So in any single equation, in any one equation that you're using, you may only have either all X variables or all Y variables. The one thing that I guess could be between the two is time, because the time in the X and the time in the Y are the same thing. So you've got to be really, really cautious about what you're doing with your equations. Be very, very kind of methodical about this. So again, step one is going to be to use vector components to turn your initial velocity into the X and Y components. All right, so some important landmarks that have to do with projectile motion. Again, we've talked about projectile motion a few times before, but let's take a look at what we've got. So if you've got an initial velocity, this would be our VI right here. This first launch velocity right here. So the couple of things to kind of keep in mind. Keep in mind that our Vx is constant, right? Vx, every single angle, all the way across, Vx is constant, because again, there is no acceleration in the X dimension. Vy, however, changes. And this changes according to what we've done in our free fall kind of problems before. VIY starts off at its maximum, but VIY gets less and less and less. At the top, VFY equals 0. But that's only the vertical dimension. At that maximum altitude right here, it becomes 0. And then our VYs become negative, because now they're going in the negative direction. So these are positive, 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 0, negative, 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 if we're going in the down direction. It's accelerating downwards. So our AY is always negative. Our acceleration is always negative 9.81 meters per second in the Y direction, always. So our VYs are going to get more negative as we're going back down. A couple of other landmarks. VFY at the top, like I said, is equal to 0, but we can also use this one at ground. VY initial and VY final are the same speed, but different directions. So our final velocity on the ground is equal to the negative initial velocity on the ground. Last thing, again, remember about time. So if we're talking about the time to top and the time to ground, that if we're saying that, from here to here is total time, then from here to the top is equal to half of that time. So depending on how you want to define it, from, ground to maximum to ground again is total time, then ground to top is half the time. Or you can define it as from ground to top as being time, and ground to ground again is equal to 2t. Either way works, but just keep in mind that you know something about the time dimension as well, that this is a symmetrical pathway. So these are some little things that you're going to have to kind of keep those tricks in your pocket to do these. It's not going to remind you in the question to keep those in mind. So here's an example of our problem that we're going to do. We'll do this as our first one, kind of walk through this and kind of how we would solve some of these different components. And then there's a second problem that follows it up. So if you need to take a break, hit pause right now. Go to the bathroom, whatever you're going to do. Go get a cat, emotional support animal, whatever you're going to get. But we're going to run through this math. So it'll take us a few minutes to walk all the way through this problem. So here we've got physics students launching a rocket at an angle of 53 degrees above the horizontal, 53 degrees up. Initial velocity of the rocket is 12.5 meters per second. That's not a real fast rocket. Again, there's a bigger, funnier picture over there on the side. It's 12.5 meters per second. Pretty slow for a rocket, actually. But so we've got some questions. How long is the rocket in the air? So that's a time. How far away does it land? That's range. And what's the maximum altitude? So those are the three things that we're going to try to solve as we're getting this. So this is time here that we're going to try to find. This is going to be dx, and this is going to be dy, right? Altitude's a y dimension, and then displacement horizontally is going to be that x dimension. So what do we know about this? So first things first, we got to take that initial velocity and we have to turn it into our x and y components. So we've got our rocket. Here it is. Our rocket is launching. Okay. If I could draw, that would be really, really helpful right now. Sorry about that. But we are launching. It is at a 53-degree angle, 53 degrees above horizontal. Again, just a regular 53-degree angle. We know that the initial velocity of the rocket is 12.5 meters per second. So that's at the angle. So we need to figure out our horizontal and vertical components. Great time for you to hit pause and go do this with your calculator so you can kind of see what it is. Check yourself to see if you get it right. So as I do this, this would be VI times the sine of my angle. Again, SOHCAHTOA. Sine gives me the vertical component, VIY. Sorry, I have a hard time with saying that and reading that at the same time. That's what I want right there. Apologies. Is equal to VIY. And if we do VI times the cosine of theta, ka, right, is the adjacent side, is going to give us VIX. So I'm going to get those two numbers plugged and chugged, and we're going to use them here in a second. So again, make sure that you're not in radians. Make sure that you're actually in degrees. 12.5 times the sine of 53 degrees is equal to 9.98. Looks like we have, well, two sig figs here. So again, VIY is going to be equal to 9.98 meters per second. VIX, 12.5 times the cosine of 53 is going to be 7.52. 7.52 meters per second. And again, because our angle is above 45 degrees, it makes sense that our Y component it's more vertical than it is horizontal because it's above 45 degrees. So these two numbers do make sense in terms of what we're doing. So I'm going to make a list of my little variables up here so I have a spot where I can write them because I'm going to need some more room to get all this thing done by the time I'm done here. All right, so hold on. All right, what do we know? What do we got? So let's see, VIX is equal to 7.52 meters per second. VIY is equal to 9.98 meters per second. So just so I've got those, so I don't lose them later, because I'm going to have to keep erasing and give myself enough space to do some work. All right. What else do we know? Okay, other pieces that we know. Acceleration in the y direction is negative 9.81 meters per second. This VIY is positive, and so is our VIX, right? It's going in the positive direction. AY is going in the negative direction, so it's going to be falling there. We don't know too much about distance for landing. Oh, actually, we kind of do. We have a kind of a cheat here. We know that the time is going to be equal between the two. So think about what our rocket's going to do. It's going to go like this, like that, right? That's going to be basically what we've got. We're going to start, and then we're going to end. So how can we kind of cope with this? We don't know how high it's going to go. We do know some things about time. We could figure out some things about how it's going to land. We're trying to figure out what this is eventually in terms of our dy. We're going to try to figure that out. We're going to try to figure out what our dx is, dx, this direction. We need to know what time is. So what are some of the pieces that we do know about this? Well, we know a few things, deciding what we want to do. Velocity equals distance divided by time. Do we have that yet horizontally? We don't know the x direction yet. We've got VI, but we don't have time. We don't have enough to make that one happen for us. So we can't really do the horizontal piece yet. We're going to start with the vertical piece. Okay, well, vertically, what do we have? Well, vertically, VF equals VI plus A delta T. This is AY. And we have the DF equals DI plus VI delta T plus 1/2 AT squared. And again, this is Y directions only, right, if we're doing Y. So we do actually, believe it or not, here's the trick, have enough information to use this one because we don't know the time, we don't know the distance yet, and we don't know the time yet. But we can use this equation, VFY equals VIY plus A delta T. How is that possible? Okay, well, what do we know? We're talking about the Y direction here. So you can pretend like it's going up and coming back down if you really want to, but the Y directions, we know that the upward velocity and the downward velocity on the ground are going to be equal to one another. Or we could say from here to here, the bottom to top. You could figure out what that one is as well. It does not matter which one you do. So I'd ask, but I don't think you guys are going to answer me which one you want to do. But you can solve this vertical part. We know what the acceleration is. We're going to solve for this. We're trying to find time. So you can either use the bottom to top, where we know VF equals 0, or you can do bottom to ground, start to ground, knowing that VI and VF are equal and opposite. So the one that students typically do is the one I'll demonstrate, which is the height to top, where VFY equals 0. That's the one that students typically choose. So let me show you that particular version of it. So in the vertical direction, now we're launching it vertically, right, this way. So the VIY is equal to 9.98. We know that VF at the top of our flight, VFY, is going to be equal to 0. And we know that acceleration negative 9.81 meters per second squared. So we can solve for time using this one. So VF equals VIY plus A delta T. So what do we got here? Get my pen. VFY, VF at the top of our launch is equal to 0 meters per second. VIY at the initial launch speed, vertical component only. You're almost never going to use that initial number, that 12.5. You almost never use that in your problems ever again. So our VIY, vertical component, we're only dealing with the Y directions right now, 9.98 upwards meters per second, plus our acceleration, which is negative 9.81 times time. So now we can kind of solve for this. Negative 9.98 equals negative 9.81 times t. And then we can just solve 9.98 9.98 divided by 9.81 is equal to time. And again, just over a second is our time. So our time to top equals 1.02 seconds. 1.017 is the actual number I got on my calculator. So that's time to top. So T to ground is just double that, times 2. I don't need a calculator for that. 2.04 seconds to ground. So those are our two important pieces, again, in terms of dealing with our times. So I'm going to add that to my list of things I now know. Okay, my list of things I now know. T to the top equals 1.02 seconds. T to the ground equals 2.04 seconds. That's an S. All right, now what? Well, now we have enough information to be able to figure out some of the other things. So how long is the rocket in the air? Well, we just figured it out, 2.04 seconds. 1.02 seconds to the top, and then 1.02 seconds back down. So 2.04 seconds is our final answer for that. So we got that one. 2.04 equals 2.04 seconds, right? All the way to the ground again. How far away does it land? dx. Okay. How far away does it land? This is horizontally. So horizontally has no acceleration. Velocity equals distance divided by time. And again, because this is velocity horizontally and this is time on the ground, that'll give us the distance to the ground. So VIX, 7.52 meters per second. Again, it's going to end at the same speed that it started at, horizontally. Horizontal component. So now I'm using my X components is all I'm using. DX is what we're trying to find. Where does it hit the ground? Divided by our total time back to the ground again, 2.04 seconds. Again, not time to the top because that's not when it's on the ground. So 2.04 seconds times 7.52 meters per second gives us a distance of 15. dx equals 15.3408 or 15.3 meters. 15.3 meters. There we go. And then the last one. What's the rocket's maximum altitude? Okay, so if we're doing maximum altitude now we're trying to find altitude is a Y, right? We're trying to go the up version of it. So we're going to have to kind of look back at our pieces of information that we've got. Now, just launching upwards, we want to find dy, something like that. What equations can we use? Well, we have a couple different equations that we could use. We could use this one, VF squared equals VI squared plus 2A delta D. Again, these would all be Y's, Y's, and Y's. Or you can use the df equals di plus vi delta t plus 1 half at squared. Kind of like this one, a little bit easier for me. So VF squared, maximum altitude. What's its velocity at the maximum altitude? Okay, maximum altitude. Velocity equals 0. Initial velocity in the y component is 9.98 meters per second, plus 2 times our acceleration, negative 9.81, times, this is a times, times distance, vertical distance. So now it's just algebra. This is squared. Oh my gosh, I almost forgot to write the squared. VI squared, don't forget that. So 9.98 squared equals 99.06, 0.6, sorry, meters per second. This is squared and everything else, equals 9.81 times 2. I'm doing the algebra on here. Negative 19.62 times dy. And then dy I can divide. 99.6 divided by 19.62 gives us a dy of 5.08. It's not a very good rocket meters. So it's not very fast. That's our vertical. So it did not go very high, kind of landed off in the distance. So we have some information about kind of what it's doing. So that's its maximum altitude. Okay. Do we have any other questions for today? DIY? Why do I feel like I did something wrong? I don't know. I'll have to look back at that. Something feels weird about this. I feel like it should be going further vertically than it is horizontally. But I'll come back and take it out. If I made a mistake, I'll look at it in the next equation. I'll post a follow-up to it, okay? All right. Last one. This will be a chance for you to kind of solve this one as well. Okay. Last one. Here you go. This is a chance for you to kind of apply what it is that we just learned about kicking a ball at an angle. See if you can kind of start to work your way through it. This one, I'm only asking where will the ball land. This is range, is what I'm asking you for. So again, take a moment, hit pause, and then start picking your way through this problem and see if you can kind of figure out how to make this one work. Okay. I'm going to start by sketching it out. There's my ball. I'm kicking it like that. That's going to be 38 degrees above the horizontal. Ball's kicked with an initial velocity of 20.0 meters per second. We're looking for range. I know I'm going to need to use components. So this is going to be the cosine. This is going to be the sine. Between the two sides, cosine's the adjacent, sine is the opposite. So Katoa, sine of 38 times 20 is going to give me VIY. Cosine 38 times 20, the initial velocity, is going to give me VIX. So sine of 38 times 20, 12.31, 12.3 meters per second. And then the cosine of 38 times 20 is equal to 15.76, so 15.8 meters per second. Makes sense. The horizontal component is definitely bigger. It's not a very steep angle, so the horizontal component makes sense. So VIY equals 12.3. VIX equals 15.8 meters per second. So again, those are the pieces you know you're going to end up needing to use. All right, well, what else do we need to know? Let's have some space. What else do we know? Well, we know that we're trying to solve for dx. So that's going to be the last thing we do. Okay, we're going to have to address the vertical component first. So we're going to have to deal with that. So acceleration in the y is equal to negative 9.81 meters per second. We don't know time. We don't know height. We don't know final velocity. We could do final velocity. We're going to need to find time. You know we are, because that's always going to be what our problem is. So what can we do vertically? Vertically, we have a pretty simple equation. VF equals VI plus A delta T. If we're doing this vertically, we can use that because we can figure out what it is. At the top of its range, we could go there. Or we could say, where does the ball land? We could say that VFY equals negative VIY if we're talking about when it's landing. I'll use that approach on this problem since I used the other approach on the previous one. Excuse me. So VIY was 12.3 meters per second. That means VF, when it hits the ground again, is going to be negative 12.3 meters per second. Again, we're asking where the ball is landing, so we might as well figure out what that time is. Our acceleration, negative 9.81. And now our time here is going to be time to ground. Again, if I'm doing this method, this time is going to be all the way back to the dirt again. So let's figure out what we got. 12.3 plus another 12.3. 3 plus 12.3 is 24.6. Negative 24.6 meters per second equals negative 9.81 times time to ground. So 24.6 divided by 9.81 gives us a time of 2.5076, 2 point that and some change. So 2.51 seconds. So it's going to take 2.51 seconds to get all the way from the top to the bottom again. 2.51 seconds. Got it. All right, well, now what? Got the vertical part taken care of. Or so the vertical part taken care of. Let's deal with the horizontal part, because that's really what we want to know. Okay, now we know that we've got our time. Time's going to be the same horizontally and vertically. Again, this is time to ground, not time to max. So we know that's time all the way back. So now we know that's our total time. So now we can do something that's got our total time, distance, something along those lines in there. What do we want to do horizontally? Horizontally, velocity equals distance divided by time. Is that what I did wrong in the last one? I bet I did. Vx dx over t. Vx equals dx divided by t. So velocity in the horizontal component times time gives us our displacement. Well, Vix, our initial velocity, was 15.8 meters per second. Our time was 2.51 seconds. That's going to give our distance to the ground. That's going to give us our dx. So 15.8 times 2.51 gives us a final distance equal to 39.658 or 30. Well, we only have two sig figs. I guess that's 40, huh? 39.7, aka 40 dot meters would be what it is. So with two sig figs, if we're going to go that direction. I've got three sig figs in my problem, so my apologies for being inconsistent on there. So there you go. That's where it's going to land, 40 meters away. And yeah, you could also figure out maximum height. You can figure out any of those other pieces that you need to get. You can figure out its final velocity, all kinds of stuff, if it's like coming back to the ground. So there you go. I'm going to look back now, and now I'm curious. Did I screw that one up? VFY. No, that one should be correct. That one should be good. I got to go figure that one out. All right, so there you go. I hope that worked for you to give you some examples of how to deal with horizontal and vertical motion and how we're dealing with projectiles that are launched at an angle. Step number 1, take that initial velocity, turn it into its X and Y components. Step number 2, make sure you're really clear which ones are the X components and the Y components. After that, it's pretty much the same. Horizontal motion is constant velocity. Vertical motion is governed by acceleration due to gravity. Be careful with your negative signs. Okay, so there you go. And I will see you guys later. Have a good one. Bye.